Today we will start a new chapter. I will talk basically about root locus. We'll start talking about root locus. Alright. So before talking about root locus, just to make sure I send you an email. Because I know some of you didn't receive. I was preparing during this weekend, let's say, 3 videos, which you know them. Those are not required for the exam.
ourselves.
Um, Here is more simulation about the anti-wind up simulation, the one we did in our last session. So I did anti-wind up simulation, MATLAB simulation, more practice in that sense. We did one exercise, remember, one simulink together. So here I did even maybe 2 more or 3 more for only your practice if you wish, but not required for the exam. Everything I added to what we did on Teams together, it's just for your own knowledge. Also, I did a
We need to specify.
wrap-up session. This is a wrap-up session on this chapter 5, PID controller design. I wrap up everything we took in this chapter. I call it session 7. It's a new session. So I didn't call it session 6 as add on to anti-wind up theory we explained here together. We did one simulation together on the anti-wind up, and here I added 2 or more MATLAB simulation for your own practice. Not required, but if you wish. Here I wrap up just as a resume and some other new things I added. Also considered like not required for the exam. If you wish, you could go over them. Basically, I did a wrap up here, so mostly you know them. And I added a little bit how to integrate in your computer PID algorithm, okay, which somehow we know it. Then in this record, uh, I was linking what I explained in previous to basically I was explaining the Arduino library, the PID Arduino library you are using, and how you could improve it, how you could add on it to make it better in case you want to improve it. Okay, so you understand the library more. Also, it's not required, but I recommend you to look at them if your time permits. That's it about the email I sent to you, in case you didn't receive. Today, we'll start talking about root locus, body plot, and lead lag compensation. Uh, so we'll start by very basic introduction. So this is an introduction. We'll go and revisit all of them later on in more details. So maybe if something you didn't understand, try to stop me and I'll be explaining to you. Any question before starting the new chapter about lead lag compensations or compensators? Do you have any comment, any question before starting? No? Okay. So what is root locus? Basically, well, you know, is a graphical method for determining closed loop stability and designing controllers. It's a graphical method for determining closed loop stability. So we know the stability in closed loop, and we can use it, this graphical method, we can use it to design controllers. So they are saying it's less cumbersome than numerical methods such as Ross-Hurwitz. Ross-Hurwitz is a numerical method used to determine stability. Uh, it's more easy than Ross-Hurwitz. less complicated. It requires less calculation. Allows engineers to see how altering system components such as system gain, like the controller gain, KP, KI, and KD, in particular, let's say about gain, proportional gain, to see how, by changing that gain, this will affect the closed loop response of a system. So how this will affect the closed loop pole location of your closed loop poles. So we'll be seeing it graphically. How by changing the gain, I will change the closed loop pole location and therefore the closed loop response of the system. So I'm going quickly over them because we'll see a lot of things about here. It's just an introduction to have a brief idea about this chapter. What is it? What it will be about. Then later on we'll go in details, explaining root locus point by point and other stuff. What's the benefit of compared to pole placement method we already did, etc. etc. So allows engineer to design closed loop compensators based on a desired dynamic response, like what we was doing before. Based on some desired response, um, you can design your controller. And same here, this method, it is somehow similar in that sense, and determines stability of closed loop system, typically done using software. Here is the point, we will learn it how to do it manually, and later on how we can use software, like something we call it CISO tool. In the past we was calling it CISO tool, so now we can still call it CISO tool. If you write in MATLAB CISO tool, so you'll find it, but it's most commonly called now control system designer app. We'll see that. So here is how it looks like, the root logs. So a single plot in the S plane. So here, that is the root logs plot. A single plot in the S plane. So you have the imaginary axis, you have the real axis, that shows location. So what it shows, this single plot, it shows the location of the poles of a closed loop system for different gain scales. So again, shows the location of the poles of closed loop system for different gain scale. Like your your gain k vary from 0 to infinity. So assuming this your open loop, that's a plant, alright. And here is again k times that plant, and here is your closed loop, r of s, y of s. So then you can find y over r. That's a closed loop transfer function. So now this plot, it's basically as you are changing the gain k from 0 to infinity and looking at the closed loop pole location, how they are moving. Like at k equals 0, my poles are here. So here's the arrow, you can see the red arrow is pointing here. So here my pole, my closed loop pole at k equals 0. So I keep increasing my k, and then this pole will be shifted maybe to here and to here, and this is at k maybe equal 3, at k equal 4 maybe here, maybe at k equal 6 I'll find my pole, my closed loop pole here and here. So then I can understand, like if I have k equals 6, my system will be unstable because my closed loop system will be unstable. So k equals 6 as a gain is not a good control because it will destabilize my system. So then I can understand, like in this case, I can design a k between 0 and the value that I get here. Yeah, so that's what is it about. So then a single plot in the S-plane that shows location of the poles, as you see, location of the poles. Those, the green, the red, the blue are the location of the poles for different gain scale, starting from 0 to infinity. So at the end, it's a locus. It's a geometric inference, right? So it's the locus of the closed loop poles location. It's the locus of the location of the closed loop poles by varying k, the gain k, from 0 to infinity. And you ask MATLAB or you learn how to draw it by ourselves, you'll be able to draw it. When all are plotted, the locations form a locus. When you plot all the poles, location of poles at different value of k will constitute a locus. Number of branches or loci, number of branches equals the number of poles. Like for example, here I have 3 branches. Then I can understand, like in my system, I have 3 poles, 3 closed loop poles. When I find y over r, the closed loop transfer function, it should be a third order system because I have 3 branches. This is a very important point. You can extract it from the plot itself. Example, in this case, third order system will have 3 branches. If it's third order, like this case. Okay, this is location for first pole, second pole, third pole. That's
بس
the
دكتور سؤال صغير.
yes.
هلا هن التو بولز عم بيزيحوا على اليمين، عم بيروحوا على الرايت هاف بلين، بس تالت بول اللي هي على الريل اكسس عم بتزيح على الشمال بنفس الوقت.
Yes, yes. Usually they move all together. Like this is it will move like this. So they start all here, and
مم.
then this is start moving this way. Start moving this way. From k equals 0, they are here at this arrow, this 3 point. Then when you keep increasing k, they will move this way. Each
اوكي
pole will take a direction, the blue and green and the red direction.
اوكي.
So as an example of system stability, taking this plant, and this plant is a second order system, and it has 2 open loop poles. If I ask you what are the open loop poles, you will tell me what are the open loop poles for this system.
-2, -3.
Yes. So -2 and -3. Then I have -2 and -3. These are the 2 stars are my open loop pole. Okay, then if I find y over u, the closed loop transfer function, then it is k s2 plus 5s plus 6 plus k. Then I start by k equals 0, and I draw the location of my pole. So I find out at k equals 0, at k equals 0, I'll be having my closed loop pole location are the location of the open loop pole, which is here and here. If I take k equal 1 or 0.5 or 0.2, so assume I take 0.2, so you put here 0.2. If you put here 0.2, first if you put 0, as I said, then this is as if it doesn't exist. So you'll have only this. If you now go and find the pole of this denominator, you'll find it. This is, you can write it as s plus 2, s plus 3. So you can check it yourself. So then you will have -2 and -3. Those are similar to the open loop. At k equals 0, it's similar to the open loop one. At k equals 0.2, so you put here 0.2 and you do it, you'll find you'll find like you'll be having pole here and another pole here, symmetric conjugate to it. And those are two poles at k equal 0.2. If you go at 0.5, if you can take k 0.5, because you want to draw the locus, so then you start varying k from 0 to infinity. So now at 0.5, if I take k equals 0.5 here, 0.5, and then I will get two poles, one here and one here. So you see your poles are moving. So now if I take k equal 2 and I find the roots of the characteristic equation, so at the end to find the poles, the closed loop pole of the system, so I find them maybe here and symmetric to it, so it's minus 1.5 means it is here 1.5 somehow approximately. So then those are your poles. So I can see that uh, my system is moving this way. Green, that's the first pole starting at here and is moving on the green line, and the second pole is moving in the blue line. So they meet here and then they move. So maybe I can find a k, again k, on which, so I can find again k on which my closed loop poles are at the same location. Of course, you can find this again k. And that's how the system behaves. So now, is there, if I ask you, is there a value of k? That's my question to you. Is there a value for k that destabilize my system?
No.
Because this is the real axis. See, this is the 0. Here is the 0. Okay, that's the real. This is the imaginary in your S plane. So is there any k I can find that make my closed loop pole location somewhere here in the right half plane?
No,
There
بس
is
it
no.
makes it more oscillatory. كل ما زدنا الكي بتصير more oscillatory.
So you
بس ما بتصير أمس.
very nice. Yeah. So regardless of the value of k, both poles, because it's a second order system, closed loop, closed loop second, both poles will always be in the left hand side of the S plane. Thus the system will always be stable, whatever value of k. Okay, so then you can understand now any value of k that may keep your system stable. In contrast to what we saw in this example, for example, there are some value of k that make your system unstable. Okay. So we'll continue with another example. Here is a third order system. Then I do the same. Closed loop transfer function, k equals 0. I have here, because it's third order system, I should have 3 branches. It was a second order system. I have 2 branches. You see the arrow like this and like this. I have 2 branches. Remember here I show you a rule. Number of branches equals the number of poles. So third order system will have 3 branches. Second order system will have 2 branches. So here third order system will have 3 branches. Because basically why I have 3 branches? Because I have 3 poles, and these 3 poles they will have locus. So each pole will follow a line, will follow a branch. It could happen they meet together, like this follows a green branch and this follows a blue branch. They meet together, but later on they will get separated from each other. So each pole, so I have 3 branches in this case. At k equals 0, maybe my pole are at k equals 0, I have this blue star here, here, and here at k equals 0. Then keep increasing k. This will follow the red branch, this will follow the green branch, and this will follow the blue branch. And this is logic because I have a third order system, so I should have 2 complex conjugate, so symmetric, and 1 real. Completely makes sense. So then k equal 2, so I find my pole are moving to the red dot, to the red dot. So then k equal 15, maybe to the purple dot. K equal 15, this is moved to here, and this moved to here. So at the limit, somehow very close to the instability region. So now I can understand if I want to design a controller with gain equal 15, I'm most likely very close to the marginally stable system. Then if I take 17 or so, I'll get unstable system. So usually as a designer, I need to find the gain that make the system unstable, which is the limit of stability. So I need to make sure I'm below it. So what if I take k equal 850? If my k equal 850 in green, so my pole are moving up to here, complex conjugate. So the system is stable or unstable at 850?
Unstable.
System is unstable.
Not stable.
Yes.
Not stable.
So that's it. For some values of k, like this example 850, 2 of the poles will fall in the right hand side of the S-plane, causing the system to go unstable. So now we understand how we can find system stability based on the root locus that we'll learn later in details how we draw it manually, then later with using MATLAB. So also in this introduction, later we'll learn on details how we design a controller using root locus. But in this simple introduction, designing according to specification. And this is very helpful if I have some specification, how I can use the root locus to design according to specification. So graphically, superimpose the requirements on the root locus plot. You see, this is my root locus plot. These are my root locus plot, which is, if you focus with me, is this blue line. Okay, this blue line. This is my system. It's a third order system. If you look at it, it's a third order system. Then I should have 3 branches. So at k equals 0, I have 3 pole here, and pole here. So now I start moving. I find the closed loop transfer function. So that this is P of S again, and this is K, gain K, and this is Y of S, and this is my closed loop R, Y over R. So I find Y over R and transfer function and change K from 0 to infinity, and at each value I draw the line. I find out when I increasing K, I have one pole that goes this way, and I have 2 other poles that they, at the beginning with small value of K they are real, then they keep increasing, they coincide to each other, then one it goes in this direction and the other it goes in this direction in a symmetric way because they are complex conjugate. So I can understand at that at the beginning this is because S, so I have, that's why I have here S at origin. Then you have value of k that makes the system unstable. Maybe with some value of k, big value, or somehow how much it is, I can get a pole in the right half plane. So now we're able to see the root locus, which is the blue one. What about the requirement? Superimpose on the plot. So now I want to superimpose on my root locus my design requirement. So assuming my requirement here are omega n more than 1 radian per second. So how to find if this is my S plane? Let's start it. If this is my S plane and I ask you to draw in the S plane the requirement for omega n more than 1 radian per second, how this could be drawn? Yeah, who could answer this question? Not
A
specific.
circle.
It's going to be a circle, right? Circle with a radius equal 1, right? So here the design requirement is drawing it. Well, they're drawing it just in the left half plane because we know in the right half plane are unstable, so I don't care about. But this is the green, the first design requirement I have. Omega n bigger than 1 radian per second means I should be outside the circle, right, Kareem?
Yes,
Because
yes.
omega n bigger than 1. So then the second design requirement is zeta more than 0.72. So if I take an S plane and I ask you who could able to answer this question, I want to draw in the S plane zeta bigger than 0.72. How we draw it? How it will be?
هلا بيتا هي كوساين انفرس اوف زيتا.
Very
So
nice.
we find بيتا قد ايه حسب 0.72 وبنرسم اللاينز.
So it will be line at the end. So then zeta bigger than 0.72 in your opinion, it is here is zeta bigger than 0.2 or in the blue zone, so the black zone or the red zone or the black zone, so blue or black zone,
I
which one represents zeta bigger than 0.72?
I
The
think the
blue?
black.
So
I think the black.
so some thinking it's the black and some other thinking it's the blue. So how we can decide then? So zeta bigger than 0.72. Let me help you. If I have a pole here, how much zeta will be if the pole are real? If the pole are real, if you have,
One.
yes, zeta will
One.
be 1. If my pole are purely imaginary, how much will be zeta?
Zero.
0. So
يعني
so
يعني كل
then,
ما زادت
yeah,
زتا بتقل البتا. So bigger than 0.72 يعني البلاك.
very nice. Because so then zeta equal 0, you are here, and zeta equal 1, you are here. So then this line, each time you increase zeta will decrease the angle. So then you are in the black region, right? So then I'm outside the region. So then these are my two design requirements. I'm outside the circle and inside this triangle, this zone. So then the white zone, so in MATLAB you will see they have this notation. The white zone is the allowed zone. So any pole that is inside this white zone is satisfying your requirement. Good. So now my question to you. This is my system. So this is my system. This is my P of S, which is 22.3, etc. And this is Y of S. And then minus plus R of S. And this is K. Alright. And this is the root locus. The blue one is your root locus. this, and this. This is your root locus. And the green and the black are your design requirement, and you should be here to satisfy your requirement. So my question to you, is there any gain I can find that satisfy my requirement?
No,
Why you think is no?
because the blue line and the design requirement area don't meet.
Very good, Kareem. That's it. Because if you are verifying your design requirement, you should be your gain. Remember, this is the blue line is the location of your closed loop pole. And to satisfy your requirement, you should have poles in this white location. And now I went from 0k, from 0 to infinity. I didn't find any pole that cross my desired region. Well, you will tell me maybe I have a pole here. Yeah, but you should have all your pole in here. Maybe when this pole is here, you have one pole here and the other one is here. So then you keep increasing, and this doesn't satisfy. Means there is no value of k that satisfy my requirement. So now if I means a proportional controller is not enough to satisfy your requirement. So you need to add integral or derivatives. A proportional controller, if you take it from 0 to infinity, is not going to satisfy your requirement, which is omega n more than 1 radium and zeta bigger than 0.72. So what I did, poles, let's read first what they are putting here. Poles must fall inside the white intersecting area. Can a proportional controller satisfy the design requirement? What is the answer?
لا طبعا
Cannot.
no.
So then maybe we'll look what they did then. Okay, then let's see what they are using. Add a lead compensator, which we don't know what is it. But well, they added a controller now. This is my P of S. They added a fit controller, they call it C of S. And this is Y of S minus plus R of S. So now they added a controller. That's the controller they add. Later on, we'll learn how to design lead and lag compensator and how they are similar to P and I, PPI or PD and so on. Or also how we can use root locus to design PI, PD control, not necessarily lead and lag compensator. And we'll see what the advantage of using lead compared to, for example, PI or PD and so on. So add a lead compensator. They added that compensator and they find the closed loop. How to get rid of this one? Hello, hello, hello.
دكتور عم نسمع.
يا دكتور سامعينك.
Okay. Uh, how to this appear? I don't know. Okay, it went out. All right. Okay, sorry guys. So now we added this compensator and I also added again K in addition to the compensator. And I find my closed loop, which is Y over R, and then I start moving K from 0 to infinity. And I draw the root locus. So now, by looking at this system at K equals 0, if you want to analyze it, at K equals 0, I have pole here, I have pole here, I have pole here, I have pole here. Well, I have 4 poles. Why I have 4 poles? Remember P of S was, if you remember it from previous slide, was S3, S2, S was something like S3 plus S2 plus S, and here something, we have something here. So you have it's a third order system P by itself. When you added C on it, it becomes fourth order system. So then in open loop you have 4 poles. So then 1, 2, 3, 4, those are the poles at k equals 0. So at k equals 0 I have this poles. Then but also I have a 0. So 0 equal minus 1 over 0.67. So and this is in this circle that you can see it here. This circle is your 0. So I have 3 poles and I have 4 poles and 3 and 1 0. So how many branches do I have? Because it's a fourth order system, I should have 4 branches. Let's see how many branches I have. So this, if you follow my pen, this 2 blue, they move, approach each other, they intersect at this point, and then they move away, they take away from each other. So then they move, they continue moving in this direction. And at the same time, this pole is moving in this direction, converging to the 0, taking his way to the 0. And this pole is taking his way to the infinity. So these are the trajectory, the locus of each of your poles. So you have 4 poles, so you have 4 branches, 1, 2, 3, 4. So again, 1, this 1 branch, this 2nd branch, this 3rd branch, this 4th branch, because you have 4 poles. So then the poles are approaching each other, they intersect, they go away. This pole is converging for the 0, and this pole converging to infinity. So then my question to you, is there my question, is there a gain k that makes the system unstable in this scenario?
I'm done
Yes,
بالنيجاتيف فنو.
yes, doctor.
Yeah, because
When it passes the
right
the right,
half plane. So there is a
yes,
value which we don't know now. It's alright, but we can see that when we draw the root locus later, we know how to draw, so we can find this gain k that makes. Then also there is some constraint on your decay. You cannot take it from 0 to infinity in this case if you want your system to be stable. But now my question to you is there a value for k that satisfy my requirement? What are my requirement? Remember, omega n bigger than 1 and zeta bigger than 0.7 something from previous slide. So that's the zeta, and this is the omega n. And we said last time is this is the white area is the area on which I should find my poles, my closed loop pole, to satisfy my requirement. So I need my pole to be located somewhere in the white area. So I have 4 poles now. So my 4 pole should be somewhere located in the white area to satisfy my design requirement. So is there a gain k I can find having added this? Now I added this compensator, so I don't have only k and p. I added a compensator. So is there a gain k that I can use in which I'm satisfying my requirement?
yes, doctor.
Yes, doctor.
There is, right?
Yes, yes.
Yes.
So here they are showing us when k equals 0.1. So we started at k equals 0 and we keep moving at k equals 0.1, I am having pole at this location, and pole at this location, and pole at this location, and pole at this location. Those are my 4 poles, and the 4 poles are in my required region, so means I'm satisfying my requirement. So that one importance of root locus is then you can put your design requirement on your root locus and design your control. So then there is a gain that satisfies my requirement. Setting k equals 0.1 satisfies the requirement. So later on we'll learn how to design this one and how to find the gain k. My point to you now is just if I ask you what is the effect of this lead compensator we added? What is the effect of it on the root locus? So look to the root locus, how it looks like without this lead compensator. And what is the effect of it when I added the lead compensator? This is my root locus after adding the lead compensator. And here is my root locus before adding. So here is my root locus before adding the lead compensator. This is the geometric before adding root locus, before adding the lead compensator. And here is the geometric, means the locus of your poles, of your closed loop poles, after adding the lead compensator. What's the effect of lead compensator on the root locus?
It makes it cover more area or more possibilities.
Yes, you can say that. So basically, it reshapes the locus. It give it another shape. And that's why we need to add lead compensator or lag compensator or derivative or integral. All of those are used to reshape the locus. So I can reshape the locus by adding a controller. This controller could be lead compensator, could be lag compensator, could be integral, derivative, PD, PI, to reshape the locus so in a way that I can satisfy my requirement. So our goal is to reshape the locus to be in the required region, in the design requirement region, so then I can satisfy my requirement. So really the idea of designing this controller is to reshape the locus to be inside the required region. That's the goal of that's it for root locus and introduction. So now we know that you have a lot of questions how we find the gain k, how we draw the root locus first, how we find the gain k, how we design a lead compensator, how we design lag compensator, how we can design PD, PI, PIT using the root locus methods. All of those still questions. When we start root locus chapter, we'll explore them in more detail. Any question regarding this introduction to root locus? Yes.
No, like
Okay. So now, of course, I'm not going to go into body plot and lead lag compensator design. I will go on root locus basics. Starting root locus basics. As always, most of my slides, some of them are taken from Prof. Richard Hill, and you have the YouTube for his YouTube channel, so you can go and explore it. So I'm taking some slides from his YouTube. Root locus basics. We will work on 4 things now. Basically, the idea of let me say the idea of this chapter is to know how to draw the root locus, and that's the learning outcome of this chapter. All right. So the learning outcome is how we draw a locus, a root locus. Drawing the root locus. That's the ultimate goal of this chapter, this small chapter. But before design for transient response. One approach to control design is algebraic approach. So one approach to control design is algebraic approach. What we mean by that, algebraic approach, it's basically what we learned up to now. And by the way, I put for you on Moodle, extra practice for PID. If you saw them, and those are solved by a student, but I checked them. I don't think like they are correct. There is nothing wrong inside. Those are extra practice. In addition to your homework, you can practice them, and they are all based on pole placement. Okay, so I put some slides from the course just this is we saw in class. All right, so basically ball placement we do or the algebraic approach is we have our requirement, we compare it to a basic first order or second order system. Like in this case, we compare whatever we have here to zeta omega n and so on. So then you can find zeta and you can find kp. So we did many of them. Like for example here, closed loop characteristic equation, it is this one. Then we do the comparison between this and the desired, the closed loop characteristic equation and the desired. Then you can get the parameter, right? So you can go over them. I think that's what we call algebraic approach. Based on your requirement, you know your closed loop, your desired closed loop location, and you compare the desired closed loop location with the closed loop characteristic equation. Okay, including your controller in it, so then you can find the gains. So for a system with closed loop dynamics that match a known simple form, first or second order system, so we can do the algebraic approach. What we do, we choose control gains to produce desired parameter values, to produce desired parameter value. So place poles in desired location to achieve transient response. And that's what we was doing in our previous chapter PID. Right, this is the algebraic approach or the pole placement approach. We call it pole placement approach because I'm shifting my pole from an open loop location to a desired closed loop location by designing a controller, by choosing gains for my controller, and doing what? This algebraic approach, the system identification. I identified them with a known simple form. And remember, sometime we have zero in my closed loop transfer function. We said, okay, as first order approximation, as a starting point, then later we need to tune. Okay, then this process is more difficult when you have a higher order system. And you saw that in one time when I explained it to you. So how to go? Uh, Maybe I don't have my hard disk now. I should. Okay, this is my hard disk. Let me. Okay, this is my. Like when I was talking here, like getting to be hard when we like. Even so, this is not so. Like you see here how we did the identification, like even it's a third order system, and then if you do the calculation, you'll find like it takes time actually. So then is there a simpler method? Root locus is much more simpler. Okay, so instead of doing the system identification, so you need a lot of algebraic you need to do. Right, so then this process is more difficult when you have a higher order system. Even so, the system I was talking about was a second order system, but the closed loop becomes a third order system, or even it was first order system, but because you have PID, you need to check it becomes third order system. So then, so what if your system is the process is very high order system? Then this process becomes more difficult and difficult to see the effects of gains on all poles. You cannot know actually the effect of gain on the all poles. Maybe you just you choose a gain that satisfies your requirement, but in root locus you can see the effect of gains on the all poles and how the poles are moving when I'm changing the gain from 0 to infinity. So I can know all the location of the poles. So I can know at which extent I will be unstable, where I will be unstable, for example, if there is instability. So then this is one advantage of root locus. Also, yeah, this advantage I want to talk about. So root locus is a graphical tool that shows how the location of the poles of the closed loop transfer function moves as a parameter is varied, like a control gain. Here up to now we are only seeing P. Gain K is moving. Okay, when I'm moving the gain K, how the location of the poles of the closed loop transfer function moves. At K equals 0, I'm here. So I move this way and I move this way and maybe different color. So here I have then two poles at the origin. Looks like I have two poles at the origin, and then when I keep increase K, they move. One black move down and the blue assume move up, and looks like here I have two poles here, one pink and one yellow, and when I keep increasing my K from 0, this is assume this will follow this trend. I don't know. It's actually the same. That doesn't matter. And the yellow follows the down circle. So then they meet here, and this will go this way, and the pink will go this way. All right. They come back and meet here. Then when they meet here, one of them will go to infinity. This one or this one doesn't matter, and the other one will come up to here, and actually it converge. There is two ways on which the poles are converging. They converge to a 0 or to infinity. So as a general rule, if you wish, the poles are converging for zeros, and if in case it go at k equal infinity, for example, when k tends to infinity, it converges here, like assume as you have a 0 at infinity. So usually the pole is attracting by a 0. Then it converge for a 0. Here converging for a 0 is going to look for 0 at infinity. He's hoping to find a 0 at infinity. So that's why he went to infinity. But this is a find a 0 here, so we go directly to the nearest 0. Okay. So helpful, this root locus method is helpful for higher order system. Like for example, the system, now I'm drawing the root locus. Can you tell me how much is the order of that system? Can you guess how much is the order of that system? So this might,
4.
it's order 4. So why the order is 4?
4 lines, 4
Because
paths.
I have 4 branches: blue, black, pink, and yellow. Right? 4 branches, 4 passes.
Yes.
So that's why it's fourth order system. Alright. So now it's a fourth order system, and by a simple click on MATLAB, I can know the effect of gain from 0 to infinity of my closed loop pole location. Is there a pole that can make my system unstable? Is there a gain that make my system unstable?
No.
There is no. So also useful for finding approximate results quickly. So quickly you can find approximate control. Let's take this example and try to draw the root locus for it. I'll go with you on my whiteboard. Root locus basic. Okay, so this is my system. We need to plot how the closed loop pole change with Kp. Well, first we need to find the open loop pole of my system. So that's the system you have in your slide. What's the open loop transfer function? Let's say what's the open
S
loop transfer
S
function?
plus 2, S plus 1.
So the open loop transfer function is S plus 2 over
S plus 2, S plus 1.
yeah, you mean
For roots.
you mean these are the rows?
Yes, S plus 2, S plus 1.
Are you sure?
No.
No, not sure. Okay, then
لا لا منن S plus 2, S
yeah.
plus 1 لا.
So this is your open loop transfer function, but this is not your open loop transfer function. What is the open loop transfer function?
Times Kp.
Times Kp.
Yes.
So maybe I didn't explain, maybe not, but let me tell you something. Open loop, the definition of open loop, just take this branch. You see my arrow where it is? Take this branch and open it, don't close. So if I open it, I'll find in my way I have Kp and S plus 2, S2 plus 2, S plus 3. So then now, if I'm having H here, okay, this is very important. If I am having H here and I ask you what is your open loop transfer function, you take the loop and you open it. That's the definition of open loop. You take the loop and you open it. Then in that case, you need to multiply by H of S as well, whatever dynamic sensor you have here. That will be your open loop transfer function in general. Okay, so
بس نحن we opened it. كيف H of S دخلت؟
yeah, but because when I open it, this is my H of S, right? So now, if you open it, your system will be Kp S plus 2, S2 plus 2S plus 3. This is your Y, and this is your H. So then the definition,
بتفلت من جهة يعني.
yeah, then the
Okay.
definition of your open loop, just you take the loop and you open it, and you take everything in your path up to here, up to this point. So then it is KPS,
Okay.
just you open your system. So here is the error. Here is, I'm not sure you want to call it Y measured. Maybe Y measured, like after the sensor, YM. This is your open loop. Okay, so now we know the open loop. Transfer function What is the closed loop transfer function? It is forward over
1 plus
1
loop.
plus loop. So then here professor he did them for us, and he find open loop as we find it. He called GOL and GCL as closed loop, and here is the closed loop. All right. So now our goal is to plot how the closed loop pole change with Kp. How the closed loop pole change with Kp. Let's take first Kp equals 0 or Kp tend to 0. When Kp tend to 0, then my closed loop denominator or characteristic equation will tend to S2 plus 2S plus 3. Agree? If I take Kp equals 0, the denominator will tend to this one, right?
بلى.
Then this has S equal minus 1 plus minus j square root of 2. These are, if I want to find the poles of this denominator, will be like how? So minus 1, so assuming this is my minus 1, and this is square root of 2. If this is square root of 2, and this is maybe symmetric to it minus square root of 2, so then those are my two poles when Kp equals 0. So now I draw my first 2 points of my root locus at Kp equals 0. And those are tends to be the open loop pole. You know, just as a rule, if you wish, you can generalize it later. At k equals 0, your closed loop pole are same as your open loop poles. Good.
Yes, yes.
Then let's take k equal 1. Now when Kp equal 1, then my closed loop denominator will be S2 plus 2 plus 1 3s plus 5. If this is equal 0, you can find the locus, the gain. So you can find the poles S. So I find them myself here and here, and this is for k equal 1. K equal 1. K equal 1. This is for k equal 0. This is for k equal 0. Then I did for k equal 2. So I get S2 plus 4S plus 7 equal to 0. Then you can find the poles. I find them here and here. This k equal 2. K equal 2. Etc. at k equal infinity. This is very important. When k tends to infinity. So what do you have in this case? At k equal infinity, your system will be equivalent to your denominator. Looking to the denominator, so let me closed loop denominator. So I repeat, so just to don't get confused. Closed loop denominator now when kp tends to infinity, kp. So then this will be the denominator will tend to kps plus 2kp. You agree? Agree or not?
بس مش we should substitute Kp by infinity.
So it's a big value, right?
Yes, it's a big
It's a
value.
big value. Because there is no number equal infinity. So it's a big value. I can neglect 2. I can neglect this in front of it. And I can neglect the 3. So I keep it this way.
okay.
So then, if this is equal 0, then
بدك تكتب الاس سكوير كمان وقتها neglect.
yes, we neglect s square because there is no, it's multiplied by 1. So
اوكي.
infinity time. So then, here I have s equal, it will give me s equal minus 2. So remember, at infinity, when my gain change from 0 to infinity, when my gain becomes infinity, my closed loop pole will tend to minus 2. So then I will go to minus 2, and here will be my pole at infinity. So now I can draw it. So, but what is the pole at infinity? It's the 0 for the open loop pole. S equal minus 2, it's the 0 for your open loop system, right?
Yeah.
So then this is also a 0 for your open loop system. And if I want to put in red my open loop pole, those are my open loop pole and my open loop 0. So now in black, I will draw my system. If you continue doing it, you will find we are starting from here, going this way up to here, and then maybe it's better to write it in different color because my S plane is in black. Then if you continue, you will find you have point here with K. At a certain K, you will be here, and in maybe green, starting from here. And if you will continue, you will see they at some K, they will meet together. And this is normal, they are symmetric, second order system. So if it's not symmetric, it doesn't make sense. And then now, one of the pole, it doesn't matter which one of the pole will converge for 0 because they see 0 here. And the other pole, he went to look for a 0 at infinity. He's hoping to find a 0 at infinity when kp tend to infinity. Okay, kp, it doesn't matter. Kp we're calling it. So that's how we draw root locus. So see, drawing it, then it's time consuming. Of course, later on, we'll teach you an approximate way to draw it by hand. And after learning how to draw it by hand for the exam mainly, we will learn how to do in MATLAB. So then you'll find you'll facilitate your life, and you don't need to draw it by hand at all. But for the exam, you need to learn it by hand. And the reason why I want you to learn by hand is it helps you understanding things, analyzing root locus if you learn how to draw it by hand. And I'm going to teach you an easy way to draw it by hand, an approximate way, not very accurate. The accurate way, it's time consuming and it takes time. I was teaching it in Singapore, it's hard. So now in this YouTube channel, from where I pick my slides, they simplified the approach, the steps. So you only have few steps which give you an approximate root locus, not very accurate and approximate. So it's not very exact method. It's an approximate way, but it's still helpful, and that's what I want you to know: the approximate way of drawing root locus. Because at the end, you will use MATLAB in your research later on, for example, or in your advanced study or in your work.
دكتور بس سؤال صغير.
Yes.
بس كيف طلع ال S equals minus 2
Yeah.
when K equals infinity?
So again, you go to the denominator, right?
Yes.
Here is your denominator. So now Kp tend to infinity, then you neglect this, and you neglect this, you keep Kps. Kps is very big value. Plus, you neglect 3 in front of 2 Kp, because 2 Kp, 2 times infinity plus 3 So big value times 3, you neglect the 3. So you keep having this denominator. So then now my denominator is, that's my denominator. Instead of having S2.
اوكي بس كيف طلع قصدي الاس ماينس 2
Yeah. Then
من بعد الشيء؟
yeah, then now you take it equal to 0 because you need to find the pole of your denominator, which is your pole, the
Yes.
root of your denominator. So then kp and the kp common, so then s plus 2 equal to 0, then s equal minus 2.
اه اوكي اوكي
Good. So then
اوكي ثانك
it's converging to a 0.
يو.
Good. All right. So now, knowing that, we'll start learn how to draw the root locus. The graph of the closed loop pole location in the previous example is the root locus plot. Can be drawn from the open loop transfer function. Can be drawn from the open loop transfer function. So how we draw it from the open loop transfer function, we'll see now how we'll draw. Now we'll learn how we draw it in an approximate way. Actually, we'll take the open loop pole and we use it to draw the closed loop pole location. In the following slides, we will learn an approximate, underline, an approximate procedure for drawing the root locus. Take the general case. Now I have plant G and I have a sensor dynamic, whatever feedback. It's not unity feedback now. I have a transfer function in your feedback. Then the open loop transfer function is G times H. Closed loop transfer function forward over 1 plus loop. Alright. Closed loop poles can be found from the open loop transfer function, that is from 1 plus GH. Why we said we can use only the open loop? Because of this. My closed loop transfer function denominator characteristic equation is 1 plus GH, and GH is my open loop transfer function.
دكتور كيف الجي اتش هي الاوبن لوب؟
Because you take the loop and you open it.
اوكي
So
ماشي.
then you get GH. Alright, so then this is your open loop denominator. That's the denominator of your well, this is a closed loop denominator. Then, assuming that a multiplicative parameter k is in G or H, the previous equation becomes 1 plus k n over d. Well, it's most probably G over H. I'm writing it in different way. I'm writing G over H this way. K n over d. I have the right to write it this way. G times H at the end is two transfer function. I can write them as k times numerator over denominator. So then this means n over d equal minus 1 over k. N over d equal minus 1 over k. So later on we will learn when we want to draw the transfer function, we will transform it to n over d equal minus 1 over k. If we have it this way, the root locus contains all points S for which this equation holds for some value of k. So that's the definition of root locus. Yeah, to explain what I just said in a minute, in our last minute, and so that's the last slide. I said we reach here now, right? N over d equal minus 1 over k. Basically, what I said means if you keep a value, if you pick a value for k, then you will find, so hear me well, so you will find a value for s that is on the root locus. So now let's take k equal 1. As simple as that. So if I take k equal 1, so then n over d equal minus 1. N over d equal minus 1 this is going to give me s equal this two values. This is because at k equal 1. So now if you want to take k equal, if you want to do the other way around, assuming you have s from the root locus, and I ask you to find k, so you can find k now. You can find the gains that give you this location. How to do that? You have s, then you replace s by here, you get k. Well, you're asking me what's n and d in this example. I was talking about general case. I need 1 minute more just to finish this sentence. I was talking about the general case G and H. Then now I went to the specific example. So what's n and d? I told you you have the right to write your GH, which is the open loop transfer function, as k or kp, or well, let me take it k, just don't get confused. K n of s over d of s. You have the right to write it this way, and we always want to write it this way. The open loop transfer function, we always need to write it k n over d. Therefore, my n of s is s plus 2. My d of s is s2 plus 2s plus 3. Always write your open loop in the form of k n over d. So then you can apply this formula to find k for a given value for s, or for a given k you can know s, and then so now you start changing k from 0 to infinity. So now I don't look at the closed loop. I don't want to find the closed loop at all. Just I have my open loop, and I keep changing k from 0 to infinity. So let's take k equal 1 and find the closed loop location. So if k equal 1, n equal minus d. So n equal minus d, you will get what? S plus 2 equal minus s2 minus 2s minus 3. Then s2 plus s or plus 3s, right? 3s, because 2s plus s plus 5 equals 0, right? And this I was finding it here when I was using the closed loop pole, but now you don't use the closed loop pole. You can get the denominator directly without using the closed loop, just based on the open loop. And this is when you compute it, you can get s1 and s2, and this is s1 and this is s2. Then later you do for k equal 2, or for k equals 3, and so on. Then you can construct your root locus based on the open loop transfer function that you wrote in this form. Any question? Sorry for being late, few minutes. Next time we will continue from there. Any question for what I explained today about how we are drawing? We're still learning how to draw it. Any question? If no question, يعطيكم العافية.